So hello everyone and welcome to our 5th Inspiration Exchange session and our first session of 2021, and Happy New Year. My name is Nick Maxfield. I'll be moderating today's session and I handle the Schaar Lab's communications. I'll also be joined by Mihaela Schaar, who will be handling oversight for this session and arranging the Q&A. And we're also joined by several of our lab members today, postdoc Ahmed Alaa and PhD students Dan Jarrett and James Jordon, who will be making presentations and also answering your questions in the Q&A. So to give you an idea of what to expect from today's session, as I think a lot of you know, the ongoing aim of Inspiration Exchange is to share and explore the breadth of topics in machine learning for healthcare and to generate new ideas for future research projects. So now we have kind of a double header of sessions, both focusing on synthetic data, this session and also next month's session. So in our 5th session today, we'll be introducing and defining synthetic data, as well as showcasing some new possibilities in the form of some of our own lab's research projects. We also have the researchers behind these projects on hand for the Q&A and discussion. And in the next session, we'll kind of be building on what we established in this session, and that includes introducing a synthetic data competition that we ran as part of the NeurIPS 2020 competition track, and talking about how this can be improved and redesigned when we plan to relaunch it at a later point this year. So to give you an idea of how this breaks down time-wise, in a minute, I'm going to play a roughly 15-minute video by Mihaela introducing synthetic data as an area. Then we will go into 3 presentations on our own lab's research projects, and this will run about 20 minutes in total. And after this, we'll go into a Q&A and open discussion where you can talk about either the projects that we've presented or synthetic data in general. Questions would be very much encouraged. And then basically we'll just wrap up with some closing words, introducing the next session. And this will happen after basically about an hour, I expect. Right, so next up, we have Mihaela's introduction. As I mentioned, this is about 15 minutes in total, and she will define synthetic data and explain basically why we need it. If you do have a question, and we do encourage you to ask questions, please post it into the Inspiration Exchange Slack channel. If you don't know what I'm talking about, the Slack workspace URL can be found in any of the emails I've sent recently on Inspiration Exchange. And we do appreciate it if you can ask your questions early on so that we have a little bit of time to prepare, and there's just a higher likelihood that we'll actually be able to get through to your specific question. Okay, so without further ado, please let me set up Mihaela's 15-minute introduction on the topic of synthetic data.
Hello. Today we are going to talk about synthetic data and how it can break the data logjam in machine learning for healthcare. Often when I talk about machine learning for healthcare, machine learning researchers are asking me how can they get access to high quality healthcare data sets. And it is my belief that synthetic data can provide an important way to get access to high quality healthcare data to generate machine learning research. This is why in the last 4 years, our research lab has done a lot of work on defining the research agenda for synthetic data and developing a variety of methodologies for this. So why do we need synthetic data? Machine learning can catalyze a complete transformation in many domains: healthcare, education, social justice, finance, etc. But machine learning researchers are hamstrung by lack of access to high quality data in these various domains. And this is the result of perfectly valid concerns regarding the privacy and sensitivity of this data. So synthetic data could offer a powerful solution to this problem. For instance, in healthcare, which is the focus of our Inspiration Exchange and the focus of our research lab, we have often the following situation. Hospitals or clinics or medical centers have high quality private medical data, and they would like to have a variety of healthcare analytics developed to empower their clinicians, medical researchers, and patients. Yet they cannot share freely these data sets with the machine learning community due to privacy concerns. So by generating synthetic medical data that fulfills privacy concerns or that deals with privacy concerns, this can be given to the machine learning community to generate machine learning analytics to empower such datasets owners. If you would like to learn more about synthetic data, going beyond the session that we are going to have today, as well as next time, I invite you to take a look at a blog which I have written a few months back about synthetic data together with Nick. You can find this on our website under Big Ideas. Today, we are going to present to you 5 different state-of-the-art methods for synthetic data generation with different types of privacy guarantees. If you would like to see all the research that we have done on synthetic data, I invite you to take a look on our website dedicated to this topic. Let us start with the focus on privacy and the challenges associated with defining synthetic data with privacy guarantees. What does it mean for data to be private? What does it mean for data to remain private even after being processed by a potential adversarial attacker? Should we make clear assumptions about the adversary capabilities, or shall we make no assumptions? Modeling the knowledge of an adversary is difficult and risky, and failing to correctly model the full extent of an adversary possible knowledge can lead to privacy concerns. This is even more challenging because adversaries can improve their capabilities both in terms of computational abilities, analytic abilities, as well as get access to a variety of data that may further improve their information and their knowledge and may improve their attacks. So is it safer then to assume that the adversary has maximum information and access to resources? Do we require strongest privacy guarantees? Do we need differential privacy? And will this lead to limited utility and fidelity of synthetic datasets? These are all important questions that we are going to explore today and next time. There is currently no universally acceptable and quantifiable definition of privacy. We have key anonymity, differential privacy, and also other forms of privacy. Data guardians and no data users are the ones who set the terms for providing the data, and they may have all different types of requirements. Also, this is challenging because regulatory efforts such as GDPR and HIPAA do not provide clear formal definition and safeguards that we can use when developing synthetic data. In terms of fidelity, this is also posing a set of challenges. How should synthetic data be evaluated? How do we tell whether a generated dataset faithfully reflects the real data? What are the factors that determine the utility of a generated dataset for a specific purpose? We do not have a single definition on fidelity. We do not want to just compare the synthetic and the real data on a feature-by-feature basis. We want to have fidelity in terms of joint distribution of features. But this is not enough. It depends on the intended use of synthetic data that we need to define fidelity, and there may be different needs for the use of synthetic data. We may want to make forecasts and predictions on the basis of the synthetic data. We may want to understand disease and disease progression. We may want to make new discoveries. In a paper a few years back, James, Jensung, and I have started to talk about how to measure the quality of synthetic data for use in machine learning competitions. What we described here is ways in which synthetic data can be used to run machine learning competitions for researchers. So it may be that, for instance, a particular medical center wants to develop analytics and wants to identify the machine learning tool that leads to the best performance for their data set. Yet they cannot provide this medical data to the medical researchers to run a competition to identify which group of researchers provides the best possible technology. Instead, we can use synthetic data to run such a competition. But if we do so, we need to make sure that the data, that when the competition is run on the basis of this synthetic data, the methods that come up first are indeed the methods that are also going to do best when applied to the real data. So we need to have good ways, quantifiable ways to measure the quality of synthetic data such that competitions that are run on the basis of this type of data are indeed going to lead to true winners for the real data. If you are interested in this topic, please take a look at our work. But it is also important to mention that in healthcare, we do not want just to do classification, regression problems, or even causality problems. We want to also solve epidemiological studies, do time to event analysis, survival analysis, identify competing risks, do time series forecast, and estimate individualized treatment effects. All of that may be needed on the basis of the synthetic data. So the synthetic data needs to be generated and quantified in terms of fidelity with respect to numerous possible usage scenarios. Let us just take the multivariate time series data. And later, Dan and Ahmed will talk more about that. It is hard to capture the temporal correlations consistently across all time steps. And it is also, unfortunately, easier to breach privacy in the time series data, as only one concurrent pair of events may identify an instance, a person, even if the entire remaining part of the time series is unidentifiable. So hence, fidelity and privacy in time series data represents an added challenge. So the desiderata in terms of synthetic data is to provide a range of concepts, metrics and assessment methods for data privacy and data fidelity. In this way, data guardians can select the sweet spot in the risk-benefit balance where high quality yet sufficient private data can be released confidently by such data owners. If we can do that, we can create then clearing houses for such healthcare data sets. The data guardians can provide to a synthetic data clearinghouse the real data, and this data can be generated and synthetic data can be generated associated with the desired privacy and fidelity guarantees that the data guardians have required. Then these synthetic data sets with privacy guarantees can be provided to a variety of data users for drug discovery, running machine learning competition, training machine learning models, doing statistical and epidemiological research, determining insurance methods, etc., etc. And then when these new healthcare tools are developed on the basis of synthetic data, they can be shared back with the data guardians for their benefit. If you want to read more about our concept of a clearinghouse for generating synthetic data, please take a look at our blog. Today, I'm going to talk about one technique that we have developed in our lab for synthetic data generation. This is for static cross-sectional data. And we call this method anonymization through data synthesis using GANs. This paper was written together with my former student, Jin Sung Yoon, and our collaborator, Lydia Dramright. As the name is saying, we are using GANs in order to generate synthetic data that fulfill GDPR privacy requirements. So our focus on generating synthetic data with such privacy requirements. And what we wanted is to provide a solution where we can provide the data owners with the ability to choose the desired risk-benefit trade-off in terms of privacy and fidelity. And we do that using adversarial training. So when we generate our synthetic data by the generated in a GAN, we have two losses. One is a discriminator loss, which makes sure that the data is generated with high fidelity. The other is an identifiability loss, which makes sure that the data is generated with the desired amount of privacy as defined by GDPR. Then the data owner can select the best trade-off between privacy and fidelity. And we can in this way improve the quality of synthetic data while ensuring that no combinations of features could readily reveal a patient identity. So I talked about fulfilling GDPR requirements for privacy. But the challenge here is that GDPR does provide guidance in terms of language. It doesn't provide a formal definition for privacy requirements. So in order to deal with this challenge, we defined for the first time an identifiability metric to formalize the concepts and the requirements of GDPR in terms of privacy. Such a definition is built on the GDPR requirement based on the probability of re-identification given the combination of all the data on an individual patient. And for that, we have defined epsilon identifiability as the probability that the distance to the closest synthetic observation is closer than the distance to the closest real observation, real patient. And when this is less than epsilon, we have epsilon identifiability. We define this notion of identifiability, hence, to address GDPR requirements and formalize these requirements mathematically. Please take a look in our paper for the formal definition. In terms of fidelity, we are generating synthetic data using GANs, but unlike standard conditional GAN framework, where, for instance, the patient's features are generated synthetically, conditioning on the patient's real variable sets. And these are predetermined variable set. In our ADS GAN, the generator optimizes a conditioning set for each patient, and it generates all components based on this. So we have a patient-dependent generation. The advantage of this is that we can generate high-quality synthetic data while aiming to preserve privacy. No feature combination could readily reveal a patient's identity. The features on the basis of which we condition change for the different patients. You can see here the performance of the ADS GAN method as compared to other methods existing in the literature, such as MED-GAN and WGAN, as well as two methods that we are going to describe next that are developed by James, Jinsung, and I, PATE-GAN and DP-GAN. You can see here that in terms of fidelity for these various data sets, ADS GAN has a better fidelity, a higher fidelity than PATE-GAN or DP-GAN. However, the advantage of PATE-GAN and DP-GAN is that they provide stronger privacy guarantees than GDPR identifiability guarantees. They provide differential privacies. And James is going to describe this in more detail in his presentation next. After this, I'd like to just highlight that next time during our inspiration exchange, we are going to go one step further and describe our NeoRIPS 2020 hide-and-seek privacy challenge, where together with collaborators from Amsterdam University Medical Center and Microsoft Research Cambridge, our lab has run competition for generating synthetic data. We are going to discuss next time how we design this competition, which posed its own challenges. And also we are going to describe how we can go beyond this challenge in better defining fidelity and privacy for running subsequent competitions. Thank you. Hello.
Okay, so next up we have several presentations by our own lab members who will be introducing some of their recent projects that they've worked on. These are 3 presentations in total and will last roughly 20 minutes. Again, if you do have any questions, please post them into the Inspiration Exchange Slack channel. And yeah, let me load up the first one. So this is James Jordon. He's one of our PhD students. He'll be introducing kind of a double header, PATE-GAN, which is related to a paper presented at ICLR 2019, and differentially private bagging, which is related to a paper presented at NeurIPS 2019.
Hello, I'm James Jordon. I'm going to talk now about PATE-GAN, one of our methods for synthetic data generation that, in particular, enforces differential privacy. The first question is, what is differential privacy and why might we want to use it? The debate surrounding the usefulness of differential privacy is massive, so for the purposes of this short presentation, I'll simply point out that many leading tech companies such as Microsoft and Facebook utilize it. The key strength of differential privacy is that it is a provable guarantee. You do not demonstrate differential privacy through empirical evaluation, but rather through mathematical proof. In addition, it makes no assumptions about the types of adversaries that may exist, i.e. it makes worst case assumptions about these adversaries. And models can be built up using smaller differentially private building blocks. As for what differential privacy actually is, it essentially says that given an algorithm M, the distribution of M's output over 2 datasets that differ only by 1 row is closed. This amounts to requiring that no individual row in a dataset can have too much influence over an algorithm's output. Formally, this is controlled by 2 parameters, epsilon and delta, that dictate just how private the mechanism is, with lower epsilon and lower delta corresponding to greater privacy. Now that we've defined our notion of privacy, how might we actually generate the data? GANs have been shown in a wealth of settings to be powerful data generation tools due to their flexibility. Unfortunately, out of the box, GANs are not differentially private, and moreover suffer from a variety of problems that are worrying for data privacy outside the realm of even differential privacy, such as mode collapse, training point memorization and regurgitation, and potential invertibility. However, if we can somehow ensure differential privacy, then we can make the GAN a powerful and private data generation tool. In our PATE-GAN paper, that is precisely what we do. We observe that the real data is only accessed during training of the discriminator and proceed to ensure differential privacy of the discriminator, which by a theorem known as the post-processing theorem ensures differential privacy of the generator too. To do so, we leverage a framework known as the Private Aggregation of Teacher Ensembles, or PATE for short, a paper by Papineau et al. We take the original data, partition it, we train a separate model on each partition, and then we noisily aggregate these teacher models to create a differentially private label. By training a separate teacher on each partition, the effect of any individual row on the final model is limited. Each teacher can only have a limited effect on the final outcome because they are each given equal weighting in the noisy aggregation, and each row only affects one teacher. To utilize PATE in our GAN framework, we take the data and partition it. Then we use each partition along with the generator to train separate discriminator models for each partition, all using the same shared generator. We use the teacher models to label some generator data to then distill this information in the teacher models into what is referred to as a student model. The student model can then be backpropagated through to the generator. Our privacy budget is used up by labeling the generator data. No other steps in this algorithm incur a privacy cost. We aggregate the privacy cost over the course of training using the Moments Accountant, a powerful differential privacy tool that allows tighter aggregation of privacy costs than other standard methods. Unfortunately, the challenge of generating synthetic data doesn't end with actually generating it. Evaluating generated data is a difficult task, with many works having proposed several metrics for doing so. In ours, we introduce a new metric, the synthetic ranking agreement, motivated by the idea that a key use case for synthetic data is to hand it out to machine learning researchers who will then develop models on it, with the final model being taken back to the real data. For this model development to be meaningful, comparisons between models on the synthetic data need to reflect the comparisons on the real data, and this is exactly what the SRA measures. In PATE-GAN, we show significantly better SRA than DP-GAN, particularly in low privacy budget settings. you want to find out more, please do take a look at the full paper and get in touch if you have any further questions. I'm now going to talk about differentially private bagging, or DP-bag, a method that improves the subsample and aggregate mechanism, i.e. the PATE mechanism used in PATE-GAN. This paper was originally presented as a poster at NeurIPS 2019. As a quick reminder, subsample and aggregate involves taking the original data, partitioning it, training a separate teacher model on each partition, and then noisily aggregating the teachers. By training a separate teacher on each partition, the effect of any individual row on the final model is limited by only being able to affect one teacher. A key limitation of this approach, however, is that any given training point is only ever compared against a small subset of the whole data. By that I mean that we can think of the teachers as making comparisons between training points, and as they are each trained on disjoint subsets of the data, a given training point is included in only one teacher's training and therefore compared only against the other data points used to train that specific teacher. Certain relationships that express themselves between particular pairs of data points might never be picked up if these training points don't belong to the same partition of the data. In DP-bag, we aim to rectify this by allowing each sample to be in k partitions. To do so, we essentially consider k copies of the dataset and partition each of these copies into different partitions. Doing so means that each sample is contained in k different partitions, each with different data points in. As we increase k, we increase the number of other training points each training point is compared against. Of note is the fact that creating k partitions does not correspond to increasing the number of comparisons k times. Naturally, some of the partitions for a given sample will contain some of the same points as other partitions for that same sample. Unfortunately, we do get diminishing returns as we increase k. We still ensure differential privacy due to the fact that we can still bound the effect of any individual sample as being able to influence at most k teachers. In fact, we enjoy even tighter differential privacy guarantees due to the introduction of additional partitions. This is because we can more closely analyze what might happen if we remove a given data point from the training data. In subsample and aggregate, it can swing one vote in n. In DP-bag, it can now swing k votes in k times n, but those k votes don't all necessarily agree in the first place, and thus the influence it can actually have is smaller than k over k times n, i.e. smaller than 1 over n. To analyze this, we must take a data-dependent approach to the privacy analysis. To do so, we developed new theory to analyze the privacy cost of DP-bag. We introduced the personalized moments accountant, which tracks the privacy cost per individual of the algorithm. Compared to the standard global moments accountant, we introduce a new factor m, which is bounded above by 1. Our personalized moment accountant is therefore bounded by the global accountant, and therefore DP-bag is guaranteed to achieve differential privacy at least as strong as subsample and aggregate, though in practice m is not always 1, and therefore the privacy guarantee is tighter. Though we did not explore it in this work, these personalized accountants also lend themselves to allowing differential privacy at different levels for different individuals in a dataset, a particular interesting area of research. Unfortunately, there are drawbacks to DP-bag. If we look at this results table from our paper, we see two hyperparameters k and n. In the standard subsample and aggregate framework, the hyperparameter n corresponds to the number of partitions, or equivalently teachers, used. This in itself is an already difficult to tune hyperparameter. In particular, any hyperparameter needs to be tuned carefully when considering differential privacy, as the tuning itself needs to be carried out in a differentially private manner, which eats into the privacy budget. In addition to n, DP-bag introduces another hyperparameter k, which makes the situation even more difficult. Fortunately, our results show that for the settings of n for which DP-bag outperforms subsample and aggregate, it does so for all tested values of k, indicating that even if we don't tune k, we can hope to outperform subsample and aggregate by using DP-bag. One drawback which we cannot overcome, however, is that the model size itself increases k-fold over subsample and aggregate. As we train k times as many teacher models, e.g. in the n equals 250, k equals 100 setting, we are training 25,000 teacher models. The final drawback is that as we increase the number of classes C, m increases as it is bounded below by 1 minus 1 over C. This means that the privacy cost advantages of DP-bag may become outweighed by the increased model size for problems with many possible class labels. That said, in the binary classification setting, we demonstrate clear improvements over subsample and aggregate. Thank you for listening. If you want to find out more, please do take a look at the full paper and get in touch if you have any further questions.
Okay, so next up we have Dan Jarrett, who's another of our PhD students, and he'll be presenting on TimeGAN which is related to a paper presented also at NeurIPS 2019.
Hi everyone, my name is Dan, and now we'll talk about generating time series data. So what's a good generative model for time series? The temporal setting is a bit different. We want to capture not just the distributions of features within each time point, but also want to capture the dynamics of those variables across time. So the main point here is that we want to use the fact that there's more information in the training data than just whether each datum is real or synthetic. We can explicitly try to learn from the transition dynamics. Now, there are two ways you can generate time series naively, right? The first is to use autoregressive recurrent networks and train them for prediction with maximum likelihood. But they tend to make big mistakes when sampling multiple steps ahead because closed loop training, which is conditioned on ground truths, does not do well during open loop inference, which is conditioned on its own previous samples. So there are many ways to fix this, like this technique called professor forcing. But these methods are fundamentally deterministic, right? And they're not really generative in the sense that you can arbitrarily sample new sequences from them. A second approach is just to use a GAN directly, right? Just make the generator and discriminator an RNN. But that just means we will be summing the standard 0-1 GAN loss, right? We're just summing those over sequences of vectors, and summing them might not be enough of a training signal to make sure that the stepwise dynamics in the data are learned. So the question is, why can't we just combine the best of both worlds? And the answer is actually, yes, we will do exactly that. As it turns out, it performs quite well and has become a very reasonable baseline for generating time series. Okay, so we want to model data with both a static and temporal component. What do we care about, right? Three things. The samples should be indistinguishable from real data. They should be distributed to cover the real data, and they should be just as useful as real data when used for the same predictive purposes. So if I trained an algorithm using the synthetic data, I ought to perform reasonably well on a test set drawn from real data. So let's put the two and two together. We'll start with a GAN. This is the global sequence level objective, right, of matching the joint distribution of all time steps together. Now, if you want to get this interpretation of minimizing the JS divergence, you will need to assume that you can get reasonably close to having an ideal discriminator. This is, again, not easy. So we'll add the local stepwise objective of matching the conditional distributions. This is much easier, right? And we know how to do this. Just use a supervised loss and you get the KL divergence interpretation. All we need is access to ground truth sequences to train on, which we, of course, do have. Here's a visual analogy. Intuitively, this kind of works like a force field, right? Each step you take is sampled new from the GAN, but if you're anywhere near a point that you've seen before in the data, you can't stray too far from what actually happened to it in real life. Now, we'll also make the assumption that the temporal dynamics lives on some lower dimensional space, right? So we have an embedding network that provides a mapping first between feature space and latent space. And this is trained using a standard reconstruction loss. This is just dimensionality reduction. Then we have the generator discriminator pair that operates in this latent space. And this is, of course, trained jointly. This is trained using a standard GAN loss, again, the usual stuff. And finally, the generator sometimes also operates by receiving embeddings of actual data, which it uses to generate next steps. This is what's different from a regular GAN, right? It doesn't just receive its own samples from before, it also receives real data embeddings to generate next steps. Then we can compare these synthetic next steps to the ground truth next steps, which additionally gives us the supervised loss. So in this way, TimeGAN is jointly learning to encode, generate, and iterate at the same time. You can take a closer look at the diagrams in the paper to see how this is actually implemented. So does it work? Long story short, right, we're running out of time here. We can somewhat verify all our criteria that this gives strong performance compared with existing methods. First, that the samples, again, are indistinguishable from real data. Second, that they are much better distributed to cover the real data distribution than other methods. And third, that they are just as useful as real data when used for training algorithms for prediction.
All right, and our final presentation is from Ahmed Alaa, who's one of our lab's postdocs, and it's on generative time series modeling with Fourier flows. And this one was actually accepted as a paper for iClear 2021 recently.
So hi everyone, I'm Ahmed and I'm going to be presenting our work on generating synthetic time series data using Fourier flows. This work has been accepted in iClear 2021 and it's a joint work with Alex Chan and Mihaela van der Schaar. So the key motivation behind our work is the need to generate synthetic time series data. And this is a very important application in many domains, especially in the medical domain where we have loads of time series data that can be shared with researchers, except that we have privacy concerns that sharing this data with researchers may leak sensitive information about patients. And there are many options to model time series data generatively, including state space models, variational autoencoders, and GANs. And perhaps the most famous option is GANs, but GANs has suffered from various disadvantages, like the fact that it models its likelihood implicitly, which makes it hard to write the exact expression for the likelihood, which also makes it hard to evaluate and optimize. And it's also known to be vulnerable for overfitting, which might violate patient privacy. So our model is based on an alternative approach known as normalizing flows. And this is an approach based on a change of variables formula for random variables. As you know, if we take a transformation of a random variable through some function, an invertible function, then we can derive the distribution of the transformed variable if we know the distribution of the original variable and the Jacobian of the transforming function. And a Fourier flow or a normalizing flow in general is just a series of functions that transform very simple distributions into arbitrarily complex ones. And these functions need to be invertible and they need to have simple expressions for their derivatives or Jacobians. So the key advantage of normalizing flows over all other generative models, whether implicit models like GANs or explicit models like variational autoencoders that do not actually have tractable expressions for their likelihood, is that normalizing flows have the exact expression for the likelihood. So if we start with a very simple distribution like a Gaussian, and we use appropriate transformations that have simple expressions for the Jacobians, then we can write down the expression of the exact likelihood, which makes it easy to optimize the model, also easy to evaluate the model after training. So the transformation that we choose for our problem is the Fourier transform. And the Fourier transform is a very popular transform in signal processing. It transforms time series or time domain signals into frequency domain signals by decomposing a time series into a summation of different sinusoids with different frequencies, and then compactly represent this time series in the frequency domain in terms of frequency components. And this is a linear transform, so there is a DFT matrix or discrete Fourier transform matrix that's applied to the input in order to obtain the output. And this matrix is a van der Monde matrix, which has nice properties. So the key advantage of using Fourier transform as a normalizing flow transform is that because the transformation matrix is a van der Monde matrix, the Jacobian is known. It's actually equal to 1. So there is no additional computational complexity entailed by using a Fourier transform when computing the likelihood for each training sample. The other nice property is that multiplication in the frequency domain is equal to convolution in the time domain. So you can actually create convolutional layers with a very small computational complexity simply by just applying Hadamard multiplication in the frequency domain. So this is a block diagram for our overall model. So we look at time series data, which can be irregularly sampled or have variable sizes. And then we fix their size by padding zeros to these time series signal and then apply Fourier transform on top, obtaining fixed length vectors for each time series. And then having applied the Fourier transform, we then apply spectral filtering, which is the layer that adds complexity that transforms the simple distributions to complex distributions. And this is a data dependent layer. So depending on the data observed, we use an R and N to create a filter that's multiplied by the frequency domain signal in the frequency domain, which is corresponding to convolution in the time domain. And then because the Fourier transform is invertible and this spectral filtering step is invertible through division, we can recover the time domain signal again. If you want to know more about our paper, please don't forget to check it out in iClear 2021. Thanks a lot for listening. So hi everyone, I'm Ahmed and
So those were our presentations, and now it's time for our Q&A session. I think most of you know the drill at this point, but again, if you have any questions, do continue to post them into the Slack chat as we go. If we choose your question, we'll ask you to unmute yourself. So please unmute yourself and then specify basically who you'd like to actually address your question to specifically. We would like to try and keep each question to 1 minute, if at all possible, so that we can allow about 2 minutes per question and answer, and hopefully get through as many of these as possible. And do remember to please remute yourself when you're done asking your question, so that we don't continue to hear you in the background as we go. Okay, so I think we have a bunch of questions already lined up, which is fantastic. Our first one is from Jana Mejaya. So Jana Mejaya, I think you actually have a few questions in the Slack chat. So if I could ask you to maybe just focus on your first two initially, and then hopefully we can kind of circle round to the rest slightly later. Please go ahead.
Thank you very much. I hope I'm audible.
Yep, I can hear you.
Yeah, so I wanted to ask, in my area, I want to do basically data augmentation using time series data. I'm not worried much about privacy, but I want to increase the amount of data. So my question is, how do I do that? Basically like augmentation for time series data. So any good resources for that?
Yes, thank you. So I think you definitely can use any model, any generative model for synthetic data to do data augmentation. I think in this case, you don't care about privacy, you just want to augment like more data to your original data set.
Yes.
So
yes,
any
yes.
generative model, so any generative model is increasing the data, right? So even if you have models that are not restricted to, that doesn't provide any privacy guarantees, you would look at the fidelity and diversity performance of these models. So you would want a model that generates diverse enough samples such that when you augment it to your data set, it's informative and can improve your modeling. And you also don't want to add noise to your data set. So you look at fidelity metrics to make sure that the generated samples are not just random noise. I think the TimeGAN model that we presented here, the Fourier flows, pretty much all models that we presented today, even the ones that provide privacy guarantees, they are capable of being used in such applications.
Okay. Thank you very much.
I encourage you to read the references in these papers if you want to have read surveys about the different types of models beyond what we presented today that you can use for different data types.
Okay. Yes, thank you very much. Thank you.
Okay, and just to add a quick note on that, if you do want to see anything related to the presentations today, then I will be uploading this whole session up to YouTube in the next couple of days, so you can always review it at any other time if you like. So I think our next question is from Jim Smith. Let me ask you to unmute yourself. Okay. And I think it's mainly for James, if I'm correct. So please go ahead.
Yeah, thank you very much. So thanks for presentation. I was wondering, as we were talking about this risk-benefit balance between the fidelity and privacy, and there was mentioned a definition for the identifiability metric, right? Which says the distance between the next synthetic point should be shorter than the real point. But that's clear. And then I was wondering how do you measure this fidelity? So the capability of the model to replicate the underlying causal structure is also a consensus on a metric for that, or do you come up with that on your research yourself?
Yeah, thank you. So I guess I'll start by saying that actually, even on the identifiability side, there's not a consensus. The notion of privacy that is to be used is a very big and open question. The one you mentioned there was the one used in PATE-GAN, Jinsung's paper, that they defined to try and align identifiability with the GDPR, like align it with GDPR. Whereas in, for example, mine and Jinsung's paper, PATE-GAN, we use the notion of differential privacy, and these are two different notions of privacy. Like it's not clear in the wider world what the correct notion is to use. So already in terms of the privacy, we're not in agreement. Also in terms of fidelity, it's not so much that we're not necessarily in agreement, but that it's more that it's actually very difficult to measure the quality of synthetic data. If you look, for example, at the wealth of GAN literature out there, you'll see that evaluating GANs is a very difficult thing to do. There's lots of metrics that people have come up with to try and do such a thing. But this is true in general. I mean, measuring the distance between two completely arbitrary distributions is difficult. And so like this is sort of what we are hoping for when we talk about fidelity. We're hoping that the two distributions, our real data and our synthetic data, are close together. But how we do this and how we determine that they are actually close together is an open question. Sort of one thing you can do is sort of look at the marginal distributions, but as Mihaela pointed out, we want to also learn joint distributions. One approach you can take is sort of training models on the synthetic data and then testing them in the real data, and you'd hope that you get some sort of good performance. Of course, this requires that you know what task or what tasks you might be interested in for the synthetic data. That is somewhat of a limitation. Similarly, one of the metrics we proposed in the PATE-GAN paper and also in our KDD paper was this synthetic ranking agreement, which is sort of comparing models on the synthetic data and then comparing them on the real data and hoping that the comparison stays the same. And this is like a different approach where you're not necessarily interested in training models on the synthetic data and then deploying them on the real data, but rather trying to identify which models might work on the real data and then actually using them on the real data rather than trying to use the synthetically trained models. These are just a few ways of evaluating synthetic data, but there are like an absolute ton out there in the wider literature, and I encourage you to mostly take a look at things like the GAN literature just to see how many there are and things like
that. Clear. Thank you very much.
Brilliant. Okay, so I think our next question is from Milan, and probably the best person to handle it is Ahmed, I believe. So please go ahead, Milan.
Hi, thanks. So part of my question has already kind of been answered by James, I think, in the last question. But so my general concern or my general direction of thinking for this kind of research, I kind of do the same thing, or I try to do the same thing for financial data. And there's a lot of talk about identifiability and what can and cannot these models do. So one of my first thinking was if to kind of find a direction of research for these kind of GAN methods is to see what they can actually do by testing like a data set from which you generate also from a data generating function that you know, and then see what GAN actually does, and then kind of iterate through that and see how you can expand it to from, for instance, start with cross-sectional data and then time series and all this. So I kind of wanted to just throw that out there and see what the opinion of the group on this was. Yeah, that was kind of it. It's more of a general idea on the literature.
Yeah, thanks, Milan. So I think that's a very important point, which is in many applications, we don't just want to generate data that looks distributionally similar to the real data, but there are some very special relationships that needs to be preserved in the data because they are very relevant to the domain, to the application that you're dealing with. So I think there are two things one can do here. In the next session, we'll talk more about evaluation of models, but one thing you can do is, especially for causal structures that you mentioned in your question, you can either look at the real data, extract causal structures from it using, for instance, directed acyclic graphs, and then try to see whether you can replicate these relationships in the synthetic data. And this can be another dimension of evaluating the synthetic data set. If you are building a model that you want to preserve with these relationships, you can actually, instead of modeling the joint distribution from scratch, you can factorize the distribution using a causal graph where you know that some relationships you want to preserve, but then you just are learning conditional distributions between different variables that have like domain-specific relationships that you already know and you want to preserve.
Yeah.
So I think augmenting very data-driven methods like GANs that are just completely domain agnostic with domain knowledge can be structurally incorporated either in the building of the model or the evaluation of the model.
Yeah.
And I think this is a very important point also in medicine, where you want the data to make sense in the sense of just preserving the relationships between different clinical variables. You don't just want to have numbers that are having similar distribution to the real data.
Yeah, I guess it's kind of related to causal discovery then, but I was just thinking if you could incorporate into your loss function that the DAG that comes out of your synthetic data should very much look similar to the DAG that you
can either incorporate it in the synthetic in the loss function, or you can actually decompose the model into different condition distributions and learn these condition distributions separately.
Very interesting. Thank you very much.
Brilliant. Okay, so I think next up we have a question from Camila, and if possible, we'd like to address this one to Ahmed. Camila, please go ahead.
Hello. I was wondering, so I think this was partially answered by the previous discussions, but I was just wondering how exactly are those synthetic time series used when, especially on the real models of clinical relevance. So if you, let's say, trying to classify disease from time series data, would you, and then you wanted to use synthetic data sets first, would you separate and have two separate models to create both positive and negative class time series, or would you use it in some different ways?
Yeah, that's a very good point. I think if you are creating a general purpose time series dataset, or any dataset, in fact, if your model is good enough, it should preserve the conditional distribution of labels given features. But if you are generating a dataset just to fit a predictive model, it can be a good idea that you either have a separate model for y given x, like label given feature, and a separate model for the features, or you can incorporate in the loss function itself additional terms to emphasize the distribution of y given x. So you are not just treating all variables, features, and labels in the same way, because in this case you may actually have a bad fit for the labels given features just because you are not emphasizing its importance in your loss function. So you may want to add an additional loss term that just focuses or gives more weight to the labels given features. So I think it depends on the goal of creating the data set. And in time series data, especially because it's a very high dimension, it is a good idea to put more emphasis on the distribution of the labels, because otherwise it may be lost in the high dimensionality of the data.
All right, so I think we only have time for a couple more questions, but next up we have Flynn. Flynn, please go ahead. And I think this one's probably best suited for James, I imagine.
Okay, can you hear me?
Yep, can hear you.
All right. Thanks for the presentations. So my question is about, I guess, using synthetic data actually for healthcare research. So it's my experience that most methods for generating synthetic data tend to produce data that has less variation in it than real data. And I guess my concern would be that if you naively use these lower variation samples for healthcare research, you would increase both type 1 and type 2 errors, kind of making conclusions aren't there, or rejecting conclusions, or rejecting hypotheses that are true. So I guess, are there any synthetic generation methods that don't have this problem, or are there any ways to adjust uncertainty estimates so that you don't draw these incorrect conclusions?
So thanks for the question. I think the main thing I'd say actually in response to this is that like we should definitely be very careful using synthetic data for pursuing actual research. And in sort of the frame of your question, you're sort of talking about discovery here and making discoveries about the data when you talk about sort of type 1 and type 2 errors. I think this is sort of partly why we defined our synthetic ranking agreement metric, which is aimed at sort of using synthetic data not as a final tool to perform research on, but as a tool to perform machine learning research within a specific domain, so that then the product of that machine learning research, say an algorithm, can be then used in the real world on the real data. In order for machine learning research to actually be carried out, us machine learning researchers need data, and we need data that sort of reflects the problems and encapsulates in some sense the problems that whoever it is might be interested in. But in order to get access to that data, there's a lot of privacy concerns. What I think synthetic data can be used for is to sort of hand out synthetic data, if you like, en masse to a large amount of people. You can then sort of ask them to work with it, and they can sort of get results and say, well, you know, my machine learning method does this well on the synthetic data, mine does this well. And you can narrow it down to a point where you have a few researchers who are showing very promising results on the synthetic data. You then go to them with the real data, and you use the real data results to sort of actually drive the research. And I think this is a particularly attractive use of synthetic data, where it's not about making sort of healthcare discoveries on the real data, but rather machine learning discoveries that we can then take to the real data and make actual healthcare discoveries. So I think that's sort of my take on that. And I think that also sort of touches a bit on Richard's question, which was going to be next.
Yeah, exactly. So basically, in the interest of time, and I hope it's okay, Richard, we sort of tried to tackle both of those questions in the answer that James just gave. And then we just, again, because we only have a couple minutes left, we kind of cut off the any new questions, but please join the next session and do ask them at that point. We do have a final question, though. That's one of the original ones we got. It's from Janamajaya again. And this is the one, Janamajaya, it's on federated learning, if you remember that one. And I think it's Mihaela is going to take that one.
Yes,
Yeah,
so
yeah.
thank you. Thank you so much for this question. So it's a question about the difference between federated learning and what we are doing here to some extent. Am I right, Janamajaya?
Yeah, I just wanted to know if you run the model locally, is it possible to run GANs on edge devices such as cell phones, or how would you counteract this problem? Because I think federated learning inherently eliminates the privacy concern.
Yeah, so thank you very much, Janamajaya. So indeed, to some extent, if you can successfully run federated learning and you are happy with such a solution where everybody keeps their data private and they just deploy a federated learning solution to learn jointly from multiple data sets, this would work. However, in many scenarios, this is not enough, because the researchers that have access to the data at one of the various locations may want to provide the data to the larger community to train it. And this is still not possible in a federated learning scenario. The data that is private will remain private. Also, one needs to be very careful, because in federated learning settings, potentially the data that is available at the different locations may be very different in their characteristics. There may be a lot of mismatches between the features, or distributional mismatch between the data in the different countries or the different locations where this data resides. So that may pose additional problems. And in those settings, solutions such as transfer learning solutions, including transfer learning solutions using GANs, some by James and Jinsung, like the radial GAN solution, may provide new solutions for problems like that. So I would say federated learning is a very good complement to generating synthetic data, and it's a good solution when that is possible. But if we want to really liberalize machine learning for all, to do machine learning for healthcare data, synthetic data may be the best solution, because then the data can be put in the public domain, the data can be aggregated, one can understand the different data sets, homogenize them, and learn across these different data, which is really much more difficult in a federated learning setting. So thank you.
Great. Okay. So I think that's pretty much all the time we have for, because it's basically exactly 1 hour now. So before I go, just a few points from me. Our next session, as I mentioned, will be also on synthetic data, and it will be in late February. I think the date we currently have penciled in is the 24th, which is just before the end of the month. A couple other bits of housekeeping or announcements. So we are recruiting PhD students at this moment. We have a handful of fully funded positions that are slated to start in autumn 2021. If you are interested, please do have a look at the URL that you can see on the slide right here. We're also recruiting a research engineer, and this is sort of a software role where the emphasis of the role is on basically bringing the lab's own research projects to life and increasing the impact they can have. There's also a URL for that right on this slide as well. The position does close on the 31st, so if you are interested, please move quickly. Other than that, if you want to stay up to date with these sessions, of course, I do send out emails periodically or messages via Slack, but you can also visit our dedicated Inspiration Exchange webpage. If you do have any friends or colleagues you think might be interested, please let them know about these sessions and share that same URL with them. And in the meantime, I'm very much looking forward to our next session in February. Thank you all so much for joining and for your questions and opinions and comments and feedback. In the meantime, please take care and stay safe. Goodbye for now.